Oh, good morning, everybody. I'm going to go straight into the presentation. Oh, that didn't work. Thank you. Thank you. Good. Right, the human lift traffic expert solves a number of equations to select a suitable installation to meet certain design criteria using a mathematical model. The expert often then has to adjudicate between several possible designs, which requires a great deal of experience and perspicacity or perceptiveness. Many lay people and also some lift industry personnel desire a simple and quick method of selection. And over the years there's been many attempts to provide this. This paper describes the historical attempts from the 1960s onwards to the present time, and the following paper will see how we've tried to evolve into an AI environment. The problem to be solved is this equation. Relatively simple equation. The right-hand side is the requirement to transport that number of people in 5 minutes. The left-hand side of the equation is what the lift system has to do to achieve this. And the classical way of doing this is in section 2 of the paper, which you will find in number 20 in your proceedings, and you might want to have that open to follow some of the references that I'm going to make. Lee Gray presented a paper last year and covered lift traffic analysis up to 1960. And it did reveal a number of attempts to provide formula and charts to select a lift installation, as some shown there on the left-hand side of the slide. And these attempts were not taken up by the lift industry and were often only known to a very small number of people. And sometimes the people involved were not lift industry people, but were interested in the problem that they were solving. Some were lift industry people who moved on to other things. It was a transitory type of activity for them. So Lee's paper last year is interesting to give you the history up to 1960. That all changed basically with George Strakosch in 1967 when he published his classical book, Vertical Transportation, Elevators and Escalators. And he utilises a table of probable stops, and that's shown in the paper at table 1, and a table of lift occupancy, which you'll see as table 2. He provides a manual method to carry out the lift traffic design, and there's an example of it at table 3. But notice that he uses 80% occupancy right there back in 1967. His method was basically a check sheet. And if Excel had been around in those days, it would have been quickly automated. The method does require some expert input to do things like rounding the numbers, adding in inefficiencies, which is all in Elevate today, and make design decisions. But what the method does provide is a calculation of the lift's handling capacity, and he states in his particular example 19 passengers in 141 seconds, or if you want to go to 5 minutes, 40 passengers in 5 minutes. Then as now, 5-minute handling capacities. Lots of the times as you go through here, you find that we are continuing with the original ideas that people have put forward. In 1972, the British Standard Code of Practice CP 407 came out. It now manifests itself as BS 5655 Part 6. The last version was 2011. It's under revision, and I'm convener of the revision panel that's going to look at this. It had the strange title of Electric, Hydraulic and Hand-Powered Lifts. So 1972 we had hand-powered lifts. It contains a lot of selection tables. I think I know who wrote them. There's a person called Frank Williams, because he presented some papers on this. And it provides values of interval and handling capacity. Example 1 is shown as table 2 in the paper, and uses 12% as the up-peak arrival rate. Then is now 12% going to be in the British Council of Officers things, and so on. And it shows, if you look at the appendix at the back of the paper, B1 reproduces the results using a spreadsheet technique. In 1975, Dos Santos and I published a paper giving the Strakosch method as an equation, and that equation is shown there. It's equation 7 in the paper. It's got a little bit modified just to change the subscripts and so on, but it's still very much used today. That's 1975. In 1984, ISO 4190-6 was published. Lifts and service lifts to be installed in residential buildings, planning and selection, and it included some selection graphs. You see one on the left there. They were very broad brush. They only dealt with residential buildings and with passenger demand of 7.5%. But all the user needed to know to actually use these graphs was the number of floors they had in the building, population, and the desired interval. The graphs were presented for 3 values of interval, 60, 80, and 100 seconds. Don't know the details of the mathematics of how these were derived, but they probably followed Strakosch as the only sort of exemplar that was available in 1984. In Table 2 of this paper standard, the average car occupancy was set at 80%. Again, we still use 80% occupancy. In 1988, the first edition of the Elevator Micropedia included a ready reckoner, and the intention of the ready reckoner was to actually allow people to quickly get a value for round trip time. This is because the lift industry doesn't like much mathematics. It likes to be able to hide that if it can, and to find it in tables and charts and so on. The ready reckoner was developed for the performance of one lift, and you had to multiply that up if you had more than one. They were included in Guide D 1993, the first edition of Guide D, but didn't appear in the 2000 edition because these calculations in the ready reckoner were based on mass, weight, and not on area. So some evolution. In the period 1965 to 1990, lift traffic designers determined a lift installation that satisfied a particular interval. And if the resulting handling capacity was equal or greater than what they wanted, that was the lift installation designed. From 1990, these requirements were reversed, and the lift designer became more interested in the up-peak passenger demand, percentage pop, and determined the installation that satisfied that value, and then had a look at the interval and decided whether that was acceptable or not. This was the first evolution, perhaps, within the lift traffic designs. I just have a short excursion into passenger capacity by mass or area, and generally it's accepted that passengers not usually board a crowded car. And Strakosch in his 1967 book observed this, that the loading of lift cars didn't meet the assumed loading based on mass. Fruin in 1971 drew a person template with a body ellipse of 600 by 450 millimeters, which came out as 0.21 square meters. And in the 1993 edition of CIVSI Guide D, an actual value for passenger capacity was shown in table 3.4 based on a body ellipse of 0.2, but with a 5% reduction for handrails in the car, which comes back out to 0.21. Now, as then, person size 0.21 meters squared for a 75 kilogram mass person. The ISO technical reports are not standards, but they're reports to indicate the thinking of standards bodies, produced in 1996 a commentary in the back of that standard. It's not of the report, it's not actually in the main body. And it said, and it's worth reading it, while the entire subject of capacity and loading was historically being treated in safety codes as one and the same, it might be more meaningful in the future writing of safety codes to cover loading as a separate issue from capacity. One refers more appropriately to traffic handling capacity, whereas the other refers to the maximum carrying capacity, which has a direct bearing on safety. Don't know the author of that, but I suggest it might be a North American, because they talk about safety codes, whereas we talk about safety standards. The latest editions of the British Council of Offices guidelines recommend area-based car selection. I think now that most people will be using area rather than mass to determine car occupancy. So this is the second evolution that I'm going to suggest, which it's important to size lifts to fit people, not to weigh them. That is, the methods based on providing the personal space which is comfortable for the person to occupy. And this has replaced the previous method of using mass and from the 1990s onwards. Second major evolution. The ISO 4190-6 standard was published in 1984. It's well out of date, obviously, and the new designation for it will be ISO 8100-32, and to aim at that, the ISO committees decided in 2014 to set up a revision group to deal with this. The main group, WG6, of this ISO committees took the view that the equations and the design process is too difficult for the layperson to apply, and that means a lift industry layperson who is not concerned with traffic design. And so the SG5 group, which had the mission to do this, published revised versions of the charts of 1984 for public comment and extended them from residential, as I mentioned earlier on, to offices and hotels. The charts are quite complex to draw, the regions overlap, and which region you end up in is a matter of judgment, and this could quite easily mean that the designer selects the wrong system. So there's a proposal to undo the clutter, the difficulty of being able to decide which of those broad regions might be used, to actually break it out into a chart which I show in the paper, where you look to the number of floors you want in the building, the population, just like the 1984, and then you just come along and slide up the graph to a particular point, and then you can see a cluster of possible configurations to use. It's then at that point you have to make a design decision. So some conclusions. The selection of lift installation requires mathematical modelling experience and judgment. Reducing the whole selection process to a graph, table or software requires choices and assumptions to be made by the person creating the tool. These assumptions may be incorrect even for the most sophisticated expert system unless the expert has ensured the software is asking all the right questions and all the assumptions made are fully understood by the person using the tool. What is needed is an expert system. The creation of this will be presented by Richard in the following paper. How am I doing for time?
Fine, another couple of minutes.
2 minutes? Oh, I don't think I can manage 2 minutes. So, a little demonstration with a bit of luck. This is a spreadsheet calculation method, and you have on your seats a yellow paper, which I'm going to try and show how you go through. This is some tables which have been extracted from the Elevator Micropedia. This is the 6th edition. The 5th edition has been now replaced by this one. If anybody wants a copy of this, I do have some with me. The challenge for this particular design is that in the top line there it says we've got a prestige office building, 10 floors, 1,000 population, 4.2 metres average interfloor distance. Now to decide on the design criteria, you look at table K, bottom right hand side, and it says for an office building a typical percentage population is 12%, and the interval should be less than 30 seconds. But to design this then, let's take an example then. We've got 10 floors. This is just, we just landed into a previous design here. So we need to put that as 10 floors. So that's the first thing we do. The second thing we do is we need to put the interfloor distance in, which is 4.2 meters. The third thing that we need to do is to decide what the speed of the lift is, and that can be determined by a table called nominal speeds, which is on table D. And as it's a prestige building, we would like to be able to travel between terminal floors in 20 seconds. And we've got a building of 10 floors, 4.2, it's 42 meters then. We want 20 seconds, so we want a lift speed of 2.1 meters a second. Well, we won't get one of those, but we could have one at 2.5. So we've made a decision now to pick a speed which is likely to give us a better result. The fourth thing we do is we decide on what the flight times are, and you'll see those in table F, because we've picked the speed, we've picked the distance. Table F tells us what the likely flight time will be, and on your sheet you'll see it's set at 6.5. The next thing we have to do is to decide on what sort of door times we would like to have for this particular system. It's an office building, so they're probably going to be 1100 centre opening doors, and you can see that we've got a closing time there of 3, and we've got a opening time of 2.5. So we fill that in. The next thing is to decide whether we have any start delays, any advance opening, and the suggestion here is that you have half a second start delay and no advance opening. They're already setting there. We then need to determine how quickly passengers are going to get in and out of this car. Table H gives you that, and it indicates 0.9 of a second. We're now ready to go, and you remember the design criteria were 12% at less than 30 seconds. You'll see the results down here. We have an interval of 27.4, and as it happens we've got a percentage of 12%. So we've actually got a design there. But supposing you'd guessed that the lift system was going to be, you're going to have 4 lifts in there, would that work? Well, we want to first of all aim at getting our percentage population down here at 10%. So what we would have to do is increase the number of people in the car to achieve that. And we got 11% by doing that. Let's try another number and see what we get. We got 11.5, try another number, 16, and we got 12%. So we have to have a car which will accommodate 16 persons to get the 12%. But now we've failed on our other criteria. We failed and got a 40-second interval. You might decide that's all right. 4 cars rather than 5 cars. But what you have done is you've increased the size, the occupancy required. You need to now accommodate 16 passengers. So the car is going to change from a 1275 kilogram car to a bigger one. To accommodate 16 passengers, you would need to look at table J, and table J tells you that you need a 2000 kilogram car, which has an capability of being able to accommodate 20 persons, and that means that we're going to get an 80% capacity factor. So I've shown you one that worked with 1275 kilogram cars with 5 lifts. I showed you one which gives you the right percentage handling capacity of 12%, but gives you an interval which you won't like. So now you make a commercial decision as to which of those two you would prefer.